Hey guys, today in this video, we will cover how the metric tensor transforms, and we will do a brief review of the metric tensor. And you should already know what the metric tensor is. This is going to be just a brief review of the tensor. So we know that if we have a vector v dotted with a vector w, the dot product is not always this summation. Or in other words, if we have v1 and v2 dotted with w1 and w2, both representing v and w, the dot product isn't going to be v1 w1 plus v2 w2. That's not always true of the dot product. And here's the reason why. It's because vectors aren't just their components. If we are going to write a vector, we have to write it with its basis. So v would be vi-ei, and w would be wi-ei. So when we multiply v dot w, that's going to be vi-ei times wi-ei. Sorry, wj ej. We should change the summations here. And then we get vi-wj times ei dot ej. And that's the definition of the metric tensor component, gij. This is the correct formula for the dot product. In fact, this formula over here only applies in an orthonormal basis, where ei dot ej is the Kronecker delta. Let's do orthonormal basis. And we can provide a proof for that right now. So v dot w would be vi-ei times wj ej, which equals vi-wj times ei dot ej equals vi-wj. This is the Kronecker delta in an orthonormal basis. And then we can change j to I, and this goes to 1. So we can only, so the dot product is only the sum of the products of the components only if our basis is orthonormal. If it isn't, then we have to account for the metric tensor component. Or in an orthonormal basis, gij is just going to equal the Kronecker delta in an orthonormal basis, such as the Cartesian basis. So that's a brief rundown of it. Now we're going to, also, the metric tensor acts on two vectors, v and w, and gives us the dot product. The dot product of v and w. That's what it does. Okay, so now we are going to find how the metric tensor component will transform when our basis changes. So first, gij equals partial r over partial ci dot partial r over partial cj. So we are going to write our basis vectors in the calculus form because we want to find how this transforms in the calculus form. Okay. And now we transform our basis to the polar basis or whatever other basis we choose. This is going to be dotted with partial In fact, we should actually use different in this index over here. Let's use A. This is going to be partial R. Sorry. So this is going to be partial. Oops. Don't know what that was. Oh, dotted with. We do the same thing here. CJ partial R over PB. Okay. And then what we do is we rearrange some of the terms to get the components in one side. Times partial R over PA dot partial R over PB. And we can immediately identify that we just we can immediately identify that this over here is just the metric tensor in the new basis, GAB tilde. That's the definition of it. So now we can multiply both sides by partial CI over partial PA and partial CJ over partial PB. And multiply both sides by that. GAB. Okay. Now we can rearrange some of these terms to make what we're doing a bit more obvious. We can rearrange this, put this over here. And we immediately find out. That these are reciprocals of each other, which means they equal 1. Which means partial CI for partial PA, partial CJ over partial PB, GIJ equals GAB tilde. And that's the transformation from the old basis to the new basis. Okay, so we can immediately identify that this is just the forward transformation of the components F I A and then F J B and then acting on G I J, which means that to get from the old basis to the new basis with the metric tensor, we need to use 2 forward transformations, which means that the metric tensor is called twice covariant. Twice covariant tensor. The metric tensor, that's what it is. In other words, we'd have to, if we have the metric tensor over here, the metric tensor, we'd have to multiply it by the Jacobian matrix or the forward transformation twice to get the metric tensor in the new basis. And here's the old basis. So yeah, that's a brief rundown of it, and that's how you find out the transformation of the metric tensor.